acknowledge the traditional owners of the lands where we are meeting today and where we all work. This presentation was a team effort with all of the rest of the Aquawatch team and the Aquawatch Data Services team, which is myself, Rob, and Timon. Rob is based in Canberra, and Timon is based in Melbourne. I am based in Adelaide. So just a little bit about me. I won't go through too much. This is the same T-shirt Paul had the other day on. I work a lot with Open Data Cube. Previously, I worked with various different open source tools. This is a pin that I didn't make, but it's I contributed to QGIS. I ported it to Windows. I worked with NASA Worldwind, which was a precursor to what Terria or Cesium is these days. In between doing geospatial stuff or adjacent to it, I worked on a couple of startups where we did Uber for trucks in Africa and Uber for mechanics in Australia. I get great discount on tires and my car getting serviced. Once upon a time, I made a pay-for-review aerial data for a commercial listed company. And these days, I help scientists scale their workflows for CSIRO. And previously, I used to do the similar things for Geoscience Australia, Digital Earth. So Aquawatch Data Services. So Aquawatch was put together after a lot of the water quality issues and fish dying issues in the river to put data from various in situ sensors and satellite imagery in a large collection, run lots of science on it, which doesn't exist yet because the data hasn't been collected, and made available for this science to be done for analysis and forecasting, and then build out pipelines for delivering this observations and forecasting products out. The functional architecture is pretty simple. Data being the new oil, you just pump a lot of it into one collection or refer to it in place with all of these initiatives from all the space agencies making data cloud ready. So for the satellite imagery section, it's quite mature. On the in-situ network side, where I started working on this project, it's not so much, especially in Australia. And then run scientific algorithms to understand what is happening now, predict into the future, create models, and deliver that through all of the apps that we love. I saw this slide at the AEO forum a couple of months ago, and I thought I'll pinch it from TerraWatch because it's sort of the space I work in. I work in the analytics platform, so it's an infrastructure project. A lot of the investment in the Earth observation industry goes into making satellites or making vertical applications, being close to the consumer, people with the money. But the thing in between, the platform space doesn't have that much investment. So it's good that we have invested in building a platform for the water quality application, and then we have invested a bit in designing satellites and sensors, both in situ and Earth observation for this particular application. If you're interested, there's an Aquawatch 1 satellite feasibility study, which has gone up with JPL. It sort of sits in a unique spot compared to all of the other satellites. It has 100 spectral bands and is sort of fine-tuned for the water quality observation use case. You have heard about the different Digital Earth platforms. So this sort of is a slide put together by my colleague Matt Paget, who looks at all of the different ones around and shows a little map of the different ones that are in play related to the Open Data Cube. So having a platform. Oh, well, you can speak to Matt about it. I guess this planetary computer. in a second. So increase the impact of the value of EO data. So essentially, if you provide a platform where a lot of people utilizing bring their algorithms to the data, you have somewhere that people can collaborate and leverage each other's results and create a pipeline of work and collaboration. So I put this in there just to address Alex's comment. Yeah, so I'm an infrastructure engineer these days in my role. So most of the time I'm wrangling Terraform and Flux and being an YAML engineer, doing Kubernetes clusters. And this sort of diagram was put together by one of the AWS architects consulting on the project. It shows all of the many three-letter components that go into making it, and each of them can become a choke point in the workflow. So you constantly look at optimizing the costs, the efficiency, the security of all of these parts, so that the scientists have like an easy time developing their water quality algorithms and science while you are corralling all of the proprietary tools and open source tools for them to make it an easier experience. The core different data collections from the EO side that's there in the Aquawatch Data Systems is what we call an aquatic atmospherically corrected data set. Because the satellites measure top of the atmosphere reflections from what's on the ground, you need to put in an atmosphere model, reflection model, in order to understand what the spectral characteristic of the thing you're observing underneath is. If you're taking a picture from close up, it's much less of a problem, but if you're going through a large amount of medium in a reflective surface like water, it's so lighting and a lot of other things come into play. We have implemented Acolyte, which has dark spectrum fitting algorithm, looks at the lowest response. So if you use a tool like DxO Optics for calibrating your cameras, you'll be like, take a picture with the lens closed. What does the sensor have? And then you can calibrate your camera's response based on that. It sort of sets a baseline. Acolyte is run over lots of pilot sites that Aquawatch is associated with. And we did a bunch of big run recently, 5-6 days ago, and filled up a half a petabyte of data with just the atmospheric correction parts. The other one, I checked in a slide from Paul. It's a bit of a meta presentation. So we worked together on the putting in the hyperspectral data support for Open Data Cube. Currently, the hyperspectral data support has AVRIS, EMIT, and Prisma sensors attached to it. And you can do something like this with the Open Data Cube to load the hyperspectral into a ZAR. You have a specific ZAR loading driver, and then you can use any sort of metadata, stack metadata that you make up to load your hyperspectral data in. It was a big step up from the X, Y, and single bands in COG to X, Y, Z, and then time, and then lots and lots of bands in the ZAR. If you paid attention to the previous slide, I was looking at the number of bands. Aquasat-1 will have 100 or so bands, or Prisma has 200 plus bands in the hyperspectral range. So some of the services that ADS provides to the scientists is the classic managed Jupyter Hub environment, where we do the builds for Acolyte or Polymer or any other aquatic at-core algorithms and provide that in a sort of a managed notebook environment. A lot of time is spent making all the Python packages play nicely so that you have a stable environment and your code runs consistently across versions. Also, because we have got lots of partners, stakeholders sharing the platform, we have a sort of a cost allocation multi-tenancy model attached to it. So you can run up your algorithms, run up big clusters, and then still have your project's budget allocated to that. So that's sort of the setup we have currently. You have access to a few hundred gigs of RAM per box, or you also have DAS clusters you can attach with thousands of nodes behind it. I think Kubernetes, we don't have multi-cluster support yet, but a single Kubernetes cluster can go up to a few thousand, 5,000 or so nodes. And then after the notebook experimentation is done, recently I've started using Peppermill to run the notebooks in production. You basically do a bit of YAML engineering or not, and you end up with lots and lots of Argo pods running your notebooks, and you can just fire those up and let them run for however long or however much your budget goes until the budget alarms start triggering. It's the easiest way to, get your credit card. One of my friends was saying, "Oh, I ran 14,000 simulations. I wonder who is getting the bill." So the Terraform these days does like a little bit of a cost estimate on the scale you have set up your infrastructure on, the maximum nodes you can spin up. So our current estimate sort of sits at $250,000 per month. So yeah, worst case scenario. But we don't actually have bars in place. We only get an alert. We don't actually have bars in place to stop the scientists from doing so, which would be good for us. We would be happy. So the other sort of scalability option for experimentation and in Argo is using Dask. We have both Dask Gateway and the more modern Dask operator in the works. So you can scale using Kubernetes native constructs as well as more Python Dask Gateway style approach. And when Dask is happily doing water quality stuff, it looks nice and pretty like that. One of the scientists sent one of the things where the Dask was getting unhappy, and there was like little scattershot chunks of data happening with lots of waiting time in between. So that's a happy Dask. That's what it looks like. One of the other scientists, when we did a pilot in Spencer Gulf, put together this nice sort of workflow of his on how he was using the DS platform. He was capturing all of the aquatic reflectances from all the different satellites we had processed, capturing in situ data from the deployments, and then writing his notebook, and then producing his outputs, machine learning or whatever was the algorithm in between to do the matching up of the in situ to the satellite, the inversion, and then prediction. We support open standards for serving out the results. We recently produced continental all-of-time MODIS-based chlorophyll and other sort of predictions. MODIS, unfortunately, is falling out of the sky, but it provides the big archive of data that you can use for training. So we have a map portal based on Terria. We also have the same services using OWS that can go onto desktop GISs. And I'm not a front-end engineer, but I do a lot of stuff hacking up Terria. So it's one of the Terria hacks I did where I added sort of graph and login to get the in situ data as a plot on the Terria portal. So there are lots of in situ sampling stations all around Australia and the world. So let's talk a bit more about the in situ part of Aquawatch. So the in situ sensing, there is a standard for OGC, I think sensor things standard. But currently the deployment uses lots of different just off-the-shelf IoT platforms that different partners take on. A couple of them are there, Eagle and Synapse. There are many others, HydroView and many other platforms for water quality sensing around. And this is just essentially a classic ETL, data engineering pipeline that regularly calls their APIs, gets batches of data, and creates a data lake from where the scientists can absorb into and assimilate with the EO data. So having this in place for Aquawatch is really great because a lot of the stuff has to be matched up between the Earth observation and in situ for the results to be trusted. A lot of the water quality managers don't trust EO in itself because of all of this atmospheric correction and low frequency of revisit and other issues. whereas the in-situ sensors collect data in a measurable 15-minute, 10-minute intervals, very time-dense. So this is sort of one of the sensors developed as part of Aquawatch called the hydrospectra. It's a hyperspectral sensor with 1 nanometer resolution and with a diffraction grating. You get little very cool spectral curves like this out of it over time, over different spectra, and then you have amplitudes per spectra. So it's very cool. Some of the tooling for the data ETL that I sort of use and develop with, and I guess a few people use this Spark for restructuring the data from coming in from the various APIs, and also doing some basic QA, removing zeros, removing outlier, very large numbers, and so on. Trino, which is essentially used for querying the data in tabular data in place from S3 or any other blob store instead of having a computational engine running. So the managed version of Trino that Amazon calls Athena, I use Trino locally to do my experiments and query structuring. And this new one, which I sort of became aware of when I started exploring the in-situ and the sensor standards in OGC, Frost. So this is done by Fraunhofer in Germany. So it's a Java-based in-situ sensor management platform where the data is stashed away in a database of some sort, Postgre or Hive or something else, and you can start push in the data via MQTT, and you can get the data out via the Sense of Things standard. So USGS has a very extensive water network, and they have set it up Frost for delivering it, and they have around 100 or 115 or so water quality sensors around the US. We actually have a hydrospectra with one of the USGS water quality sensors in the Sacramento Bay. So that's very, very cool. One day maybe we'll have something dense like this in Australia or have it integrated like this in Australia. I believe the states have different sensors, but it's not pulled together by a national agency yet using an open standard. So there are a couple of ones we have in the Aquawatch program. You can see in here in the Fitzroy Keppel Bay area, Fitzroy River Keppel Bay area, just showing different parameters being measured over time. You can see the salinity one in there, where the ocean salinity definitely is higher, so I guess it's working. One of the other sort of showcase portals, custom portals we are building is for algal blooms using the EO data and the in-situ sort of calibration, validation to look at time over time, different extents of NDCI in lakes, and then providing alerts. So I'm almost done. So this is some of the good stuff that makes me happy, that feedback I get from various scientists using the platform. Lachlan Phillips I'm actually catching up with him later today. He's based in Hobart. He is an early career researcher. So he basically got started using ADS and started creating hundreds of GPU clusters, doing his machine learning stuff. And that was really good that we had built a platform that was easy to use, and people with little experience in cloud or could put together their science in it. So this is sort of a very text-dense slide, but the highlight essentially is we are managing a lot of data, a lot of users with around a couple of staff. So this shows if you have your stuff infra-coded, you can have a very high leverage in the amount of people you can serve. And if you have any water quality science stuff, I'm happy to partner with people, bring their science into the IDEAS platform, and put various data sets together for it, or in-situ networks wired up to it. So I'm looking for those types of opportunities. Yeah, happy to take questions.
Thank you. Are there any questions? Don't be shy. Go, Alex.
I just love how you come up with new technologies that I've never heard of. I feel like I'm kind of on top of things, but paper mill, Dask operator, Trino being actually what Athena is, it's great. Thanks for teaching me new things, Tish.
No worries.
All right. Thank you very much, Tisham.
No worries.